Alrighty, I just wanted to go over the lesson for 2.19. We have already done 2.18, and that was just introducing the concept of an inequality. We talked about the fact that not all situations in the real world could be modeled as equations. For example, we talked about the fact that you can start voting in the United States at the age of 18, but if you wrote out an equation to model that as x equals 18, that would be saying that 19, 20, 25-year-olds, 40-year-olds, none of them can vote, which is not correct. So we needed to have a different way of modeling the situation, and that would be an inequality. Just saying x is greater than or equal to 18 models all of the ages such that you're going to be able to vote. So we are looking more at the solutions of these inequalities now. The start thinking part had two different inequalities, and it was asking for the students to come up with any numbers that would make these true. The first one was an easier one. Students just came up with numbers that would make this true, and any student that gave me a number of 9.2 or less would be a solution to this because it would make the inequality true. The next one was a little bit trickier. Students actually had to guess and check and find different numbers that would work. And in the process of doing that, what they found was that the number that basically is where the solution started, meaning where all the numbers that would make this true started, was 1. So 1 would not be good because 3 minus 1 is 2, and 2 times 7 is 14, and 14 is not greater than 14. But what they found was that any number less than 1 would actually make this true. So what that meant was that you have this inequality in number 2, and it is going to be equivalent to the inequality x is going to be less than 1. So any thing that would be a solution to x is less than 1 would also be a solution to what we had right here. So we're kind of talking about solutions to inequalities. We also discussed that in the real world, there's a lot of times where you're going to have to put some money up front and then hopefully be able to save money in the end or make more money. For example, if you decide to go to college, then you are going to be paying money for college and you're not going to be able to really work much during those 4 years. But the hope is that the amount of money that you would end up making after going to college would be much more than you would have made if you did not go to college. But there's going to be a time where you would have made more money doing one thing or more money doing another thing, and that's a good opportunity for you to use inequalities. So here's the situation. It's talking about a teacher trying to figure out where to do their field trip, whether it's going to be Orchard A or Orchard B. It seems like a common sense thing. One of them is only $9 and one is $10 per person. Obviously go to Orchard A. But there's a catch. Orchard A, you have to have 3 chaperones, and Orchard B, you only need to have 1. Maybe Orchard A has a river that goes through it and they require more adults to be there so that nothing's going to happen to the kids. So you have to account for that. What the students did was they tried to figure out when it would be better or if it would be better to go to Orchard A or Orchard B if there was 8, 12, or 30 students. And they basically said, all right, well, if there's 8 students, you have to add the 3 chaperones. So for the first place, you have to pay for 11 people, whereas the other one, you'd only have to pay for 9. For 12 people, it would either be you're paying for 15 or 13 because it's 3 chaperones or 1 chaperone. And what they found was that for 8 and 12 students, Orchard B was better. But when they were at 30 students, Orchard A was better. So what's interesting here is that if you said, what is the better option? The answer would be, it depends. And it depends on how many people are actually going to figure out what is the better deal. We then went and looked at part 2. Part 2 says to figure out and to compare the 2 options, the teacher writes the the equation and the inequality. It then says, what does n represent? And when we look at this, n is just talking about the number of students. So the left-hand side would be the total cost at Orchard A, and the right-hand side would be the total cost at Orchard B when you're accounting for having to pay for chaperones as well. It says, what is going, in the situation, what does the equation 9 times x, or n plus 3 equals 10 times n plus 1 mean? And that is when you are trying to figure out when the price is exactly the same, when it doesn't matter. How many students? If you have this certain number of students, it wouldn't matter if you went to Orchard A or Orchard B, it's going to be exactly the same. What is the solution to the inequality of 9 times n plus 3 is less than the other one? That is saying, when are you going to pay less going to the place that requires 3 chaperones rather than 1 chaperone? And what you can do is you can just solve it as if it's an equation. And when you solve it as if it's an equation, you end up getting 17. And what that means is that 17 students, it does not matter. You can go to Orchard A or Orchard B. You're going to pay exactly the same price. What that means is obviously then in one direction, having less than that number of people, or the other direction, having more than 17, Orchard A or Orchard B will truly be better. You'll have to figure out which one it's going to be. And so what we ended up doing was testing a point. We said, let's just test 18. So we tried 18 students. And when you put 18 students in for the $9 place versus the $10 place, you find out that the $9 place is cheaper. So 18 is a solution to the inequality in part C. 18, if you have 18 children, it actually becomes less expensive to go to the place where you did have to pay for more chaperones. So since 18 is a solution, that whole side will be solutions. We knew that it was either going to be above 17 or below 17, which was going to be better for the $9 per person place. And we found out that since it is above 17, we shaded all of those because all of those are going to be solutions. Now we're going to be getting more into how to solve inequalities soon, but I just wanted to go over the basics. When you're solving an inequality, it's almost exactly like solving an equation. So you do all the same steps, except for there's one difference. To show this difference, I came up with an inequality. 10 is less than 20, which is true. It has a truth value of true. If you add the same number to both sides, let's say you added 2 to both sides, it stays as true. And what that tells you is that you are able to go over and add whatever you want to one side as long as you add it to the other. Then we subtracted 2 from both sides, and we still got a truth value of true. So we see that we can subtract the same thing from both sides, and we get a truth value of true still. So that's totally legal, just like it would be with solving an equation. Then we multiplied by a positive number. We multiplied by the number 2. And you get 20 is less than 40, which is also true. And that tells you can multiply by any positive number as long as you do it on the other side. Now this is where it gets a little tricky. If you multiply by a negative number, you end up with negative 20 is less than negative 40, which is false. So it went from being true to being false. And the only way that you can keep it being true would be to switch your symbol. And what that tells you is when you are solving an inequality, you solve it just like a normal equation, but if you multiply or divide by a negative, you have to switch your sign. So if it was negative, make it positive. If it's positive, make it negative. All right, after that, the students went over and solved these 3 inequalities. The first one, you just solve like it is a normal equation. You subtract 1 from both sides, and since that's not multiplying or dividing by a negative, you do not have to switch your sign. And then when you divide by 2 on both sides, that is not multiplying or dividing by a negative, so you do not have to switch your signs. The second one, when you go over and you add 4 to both sides, you do not have to switch your sign, but when you divide by negative 3, you do have to switch your sign. But what that's basically saying is any solution to that new inequality, x is greater than negative 4, is also going to be a solution to the original inequality. So that's saying negative 4 is not a solution, but any number slightly bigger than negative 4 will be a solution. For number 3, you are going to subtract 2 from both sides, don't have to switch the sign, and then you divide by positive 5 on both sides, and you don't have to switch the sign. Even though that is a negative 23 and then it becomes a negative 25, even there's a negative in the problem, since you're not multiplying or dividing by a negative, you do not switch your sign. This problem right here was talking about a person who had 2 different options for a job. One paid 18 bucks an hour and they gave them $33 towards transportation. The other one was $7.5 per hour and then they got $50 an hour in tips, but they had to split it between 4 different people. They give you the equation that would represent this. And basically what we did was instead of having it as an inequality first, it's written as an equation. And we know from a previous problem, we talked about the fact that this is basically determining the number where it would not matter which one you went with, you would end up with the same exact amount. So when you solve this, you get 16.5 hours. And what that means is that 16.5 hours, it does not matter if you go with job 1 or job 2, you will make exactly the same exact amount. Now, what that means is that if it's below 16.5, one of them will be better. And if it's above 16.5, the other will be better. But the cool thing with this is this shows where that happens. Where does it actually matter whether you are going to be having job 1 or job 2? We know 16.5 does not matter. And then what we're doing now is we're looking at what happens when it is below or above. When it is below, if you take a number less than 16.5 and put it in, substitute it in, you're going to find that the $18 an hour job will be better. You can pick any number under 16.5. So the easiest number I picked was 0. When you put in 0 for H, you're going to have 0 on one side and 33 on the other, which means the $18 an hour job is better at 0 hours, which means everything less than 16.5, since 0 is less than 16.5, all of those would mean that it was better to go over and have the job $18 an hour, and anything above 16.5 hours, it's going to be better to have the $7.50 plus tip job. When we're looking at this and we're trying to figure out which one is the graph that matches this, the top one is saying, when will it be better to go over and do the $18 an hour job? When will that be bigger? And we learned that it's going to be bigger when it's less than 16.5 hours. And when is it going to be smaller? Meaning, when is the 7.5H plus 50 over 4H going to be the better option? It's anything over 16.5 hours. So that would be that top graph. Now let's take a peek at the homework. The first one was just asking which ones are going to be solutions to this inequality. So what I did was I went over and substituted in the numbers and saw which ones make a true inequality. And I found that B and C were the ones that make a true inequality. Another way you could have done this is set it equal, found out that -2 is that place where they are equal, and then you can kind of use that. The only tricky part here is that it is less than or equal to in that inequality. So -2 it seems like that break-even point where the two sides are equal. So that would make it true because it's less than or equal to. Two answers are B and C. On number 2, the first one, nowhere in the process do you multiply or divide by a negative, so the sign stays exactly up. Let's see, that one is incorrect. Sorry, I accidentally switched the sign for some reason. I don't know why. But that one is supposed to be x is less than -26. I think I stared off and forgot what I was doing. Anyway, since you don't multiply or divide by a negative, it should be x is less than -26. The next one, you do go over and multiply or divide by a negative, so you do have to switch your sign, and you end up getting x is less than -4. And the next one, when you distribute, you combine, and you solve, you do end up multiplying or dividing by a negative, so you do have to switch your sign. Once again, make sure you guys know that number 2A is supposed to be flipped. It's supposed to be x is less than -26. On the next problem, it's saying when will they be equal? So I changed out the inequality sign for an equal sign. I solved and I got -5, and that tells me that at -5, both sides are going to be equal. And that's basically where my solutions will start. When the numbers are larger than -5, I find out that all of the numbers greater than -5 will be solutions, whereas all the numbers less than -5 will not be solutions. And that led me to be able to make my graph, which is saying that -5 is where the solutions start, and it's going to be all numbers greater than -5. On this bottom one here, they're asking you to figure out which graph. You can either go over and test points that are shaded and make sure that they're all solutions. That's one way to do it. Or for me, I just went over and solved it. And when I solved it, I got x is less than 3.5, and the graph that showed a bunch of stuff shaded less than 3.5 was D. Number 5 says that Noah is solving the inequality that you can see. First, he solves the equation, and he gets x equals 6. How does the solution of this help Noah solve the inequality? Well, we know that solving for equals is going to tell you where the solutions start. So that point, x equals 6, is where the solutions are going to be starting in one of the directions. If you just solve this, you will end up getting either x is greater than 6 or x is less than 6. I did not go over and solve it, so I don't know which one it is, but we know that 6 is where the solutions start. And then you could always test a point greater than 6 and see if it's a solution to tell you if it's x is greater than 6, or if it's not a solution, it's going to be x is less than 6. This last part here is talking about this graph. We are trying to solve the inequality 5x plus 1 is greater than negative 2x plus 15. So what I did was I made both of them equations, and after I had them all both being equations, I graphed it. And the first question says, at what value of x are the y's going to be the same? And the y's are going to be the same. You can't really see it in here, but you can see it on your copy. The y's are going to be the same at x equals 2. So that is where they would be the same, where one is not bigger than the other. And then the question is, for the 5x plus 1 to be higher than the other line, aka the y's are all bigger, would that be the values bigger than 2 for x or lower? And we found out that it was the x value is bigger than 2. So what does that tell you as an inequality? The inequality is going to have a solution of x is greater than 2. Thanks for watching.